Hello friends, welcome to my channel. Today I am going to explain you about classification of fluid, that is Newtonian and non-Newtonian fluid. In the previous lecture I explained what is Newton's law. You can watch by going through a channel link, or the name of the channel is Mechanical Mind. The name of the channel is Mechanical Engineering Concept. You can go through this and watch the previous video. So let's we start with the Newton classification of fluids. So first I am going to explain you Newtonian, and then after non-Newtonian. So Newtonian fluid follow the Newton's law of viscosity du upon dy. So we can write in term of equation y is equal to mx. So this is the line of a straight line. Equation of the straight line, this is passes through the origin. So this is tau, this is d phi upon dt. So this is mu according to Newton's law. The fluid are known as Newtonian fluid, which follows the Newton's law. According to Newton's law, the relation between tau and the rate of shear deformation is straight line, and this show the viscosity. And what is the case for the non-Newtonian fluid? Non-Newtonian fluid, we can write the equation tau is equal to a plus b du upon dy to the power n, because we draw the various cases. I am going to draw, suppose this is Newtonian fluid, this is non-Newtonian, this is another non-Newtonian, this is another non-Newtonian, this is another. So for this is the equation for the non-Newtonian fluid. So first I am going to explain you the non-Newtonian fluid. We studied non-Newtonian fluid in two types. First one is flow dependent, and second one is time dependent. For flow dependent, we take the value of a is equal to 0. So for flow dependent, the modified equation will be du upon dy to the power n. So this is the equation for the flow dependent. And for, so first we understand flow dependent. Are two types. First one is dilatant, second one is pseudoplastic. For dilatant, we can write the equation. First we expand this equation. If I expand this equation, what is B? B is known as consistency index, and N is known as flow behavior index. It decides the flow, because if n, the value of viscosity depend. If I want to modify this equation, then I can modify this equation like this: tau is equal to v du upon dy to the power n minus 1, or du upon dy. So 1 get cancelled, n will remain. So this is modified equation. So this term is known as mu apparent. So we can write tau is equal to mu apparent du upon dy. For dilatant, I am going to explain from from here I am going here. So for dilatant, if we write for dilatant as the flow mu apparent, I am going to take only mu apparent, and after that I am going to discuss only mu apparent. According to mu apparent, we can decide the flow behavior of the fluid. So mu apparent, what is K du upon dy to the power n minus 1. For dilatant, we can write n is n minus 1 is greater than 0. So n will greater than 1. So what will the graph if we want to draw? This is Newtonian fluid and this is dilatant. This is dilatant. As the flow will increase or rate of deformation will increase, the viscosity of the fluid will increase, because here the value of n is greater than 1. So as the rate of deformation will increase, then the viscosity of the fluid will increase. So this value will increase. According to this, mu apparent will increase. For this dilatant, mu apparent will increase. We talk about second case. Then according to second case, mu apparent, this is known as for the pseudoplastic. For pseudoplastic, mu apparent K or B we can write. Here we can also write B du upon dy to the power n minus 1. For pseudoplastic, n minus 1 is less than 0. So n will less than 1. So as the rate of deformation will increase, the velocity of mu will decrease. So the velocity of this will decrease, and the mu velocity, the value of mu will also decrease. So as the rate of deformation will increase, the mu value will decrease for the pseudoplastic. The example of the pseudoplastic is blood, milk. These are the practical example and asked question in GATE and ES. So the example of the pseudoplastic is blood, milk, polymer solution, colloidal solution. And for the dilatant, the example is honey. Honey is the best example. So this is for the dilatant, and this is for the pseudoplastic. For dilatant, as the rate of deformation will increase, mu will increase. For pseudoplastic, as the rate of deformation will increase, mu will decrease. The next one case is for the this is time dependent. For the time dependent, in this first one is Bingham plastic. For time dependent, we can write the modified equation tau is equal to a plus b du upon dy to the power n, or a will become tau naught. This is known as yield stress. We take example of toothpaste. Toothpaste is the best example. To maintain the flow, first we have to squeeze some amount of the tube to push outside the paste, and this squeezing to push the outside is known as yield strength. We have to push up to yield strength, then paste will come outside. So if we draw, so this is Bingham plastic. Or we can write ideal plastic fluid, ideal plastic. So we have to squeeze up to tau naught, up to yield stress, then the behavior of this fluid will like Newtonian fluid. So the only difference of tau naught in this equation, in this for Bingham plastic, and remaining will same. So if we modify this equation, then this will become tau is equal to tau naught plus b du upon dy to the power n minus 1 This is, as you know, mu apparent du upon dy. So next one case for the same, for this fluid is known as rheopactic, and this is known as thixotropic. For same case, if we take rheopactic, for rheopactic, if we take this equation, then n minus 1 will greater than 0, so n will greater than 1, so we have to squeeze up to yield stress. Then after that this behavior will increasing of mu, means as the rate of deformation or velocity gradient will increase, then the viscosity of this fluid will increase, means mu will increase. The best example of this is gypsum printer ink. Best example is printer ink. For the printer ink, we have to squeeze up to some limit. After that, as the rate of deformation will increase, then the mu will increase. So this is rheopactic, as you can see. Next one is thixotropic. What is the case of thixotropic? N minus 1 will less than 1, so n will less than 1. If we put the value in this equation, then the rate of deformation will increase, then mu will also increase. The best example of the paint. Initially, if we mix the paint, the viscosity of the paint will very high, so it rotate tightly, but after some duration of time, the viscosity of the fluid, sorry, here what I explained, as this increase, mu will decrease, so this mu will decrease. After some time, you can rotate the paint freely due to the velocity. At the rate of deformation will increase, the mu will decrease, so after the some time you can draw it easily, but initially you have to apply yield stress. Up to yield stress you have to rotate this paint. After this it will acquire the velocity. So as the rate of deformation will increase, this viscosity will decrease, so you can rotate freely. But in case of printering, at rate of deformation will increase, mu will increase. But for the, what is the case for the Bingham plastic? For Bingham plastic, up to yield stress you have to squeeze. Best example is toothpaste, and after that it will act like a Newtonian fluid. So this is about the non-Newtonian and Newtonian fluid. If we draw in a one table, then we can draw like this. This is pseudoplastic. This is a dilatant up to this downward. This is Bingham plastic, this is thixotropic, and this is rheopactic. So this is about Newtonian and non-Newtonian fluid. Hope you have enjoyed this video. Thanks for watching. I will join you in the next lecture. Thank you.